What is overfitting? It sounds like a technical term, but it is actually a very simple idea and one of the most important concepts in all of machine learning. Here is the short version. Overfitting happens when a model learns the training data too well. So well that it memorizes the noise, the quirks, the random accidents in your data, and then fails completely when it sees anything new. You can have a model scoring 99% on your training set and 63% on the real world. That gap is overfitting. That gap costs you the entire business value of the model. By the end of this video, you will understand exactly what causes it, how to detect it from your loss curves, and 5 proven techniques to fix it. Let us start with the most intuitive way to understand it. Imagine 2 students preparing for an exam. Student A finds all 500 past exam papers and memorizes every single answer. Every question, every answer locked in memory. On the practice test, they score 100 out of 100. Perfect. Then the real exam arrives. New questions. Different phrasing. Fresh problems testing the same concepts. Student A scores 41 out of 100. They memorized answers. They never understood the subject. Student B studied the same 500 papers but focused on understanding the concepts behind each answer. On the practice test, they score 87. Not perfect. But on the real exam, new questions, different phrasing, they score 85. Almost identical. Because they learned the pattern, not the specific answers. That is exactly what overfitting is in machine learning. Student A is your overfit model. Student B is your well-generalized model. The practice exam is your training data. The real exam is the world your model actually has to operate in. Let us make this visual with a concrete example, predicting house prices from size and location. Here are 15 data points. Each dot is a house. We want to fit a curve that explains the relationship between the features and the price. First curve, a straight line. This model is too simple. It cannot capture the actual curve in the data. It misses the pattern almost everywhere. This is underfitting, too simple, too much bias. Second curve, a smooth, gentle arc. This model captures the real shape of the data without chasing every individual point. Give it a new house it has never seen, and it will make a reasonable prediction. This is a good fit. Third curve, a wild wiggly line that passes through every single data point exactly. Train accuracy, 100%. But look at what it does between the points, it swings wildly up and down to hit each training example precisely. Give it a new house, and the prediction could be anywhere. This is overfitting, too complex, too much variance. The goal is always the middle path. Low error on training data and low error on new data. A small gap between the two. There is a formal framework for understanding this tension. It is called the bias-variance trade-off. Think of an archery target. You are trying to hit the bullseye, the correct prediction. Top left, low bias, low variance. Your arrows cluster tightly on the bullseye. This is what you want. The model is accurate and consistent. Top right, high bias, low variance. Your arrows cluster tightly, but in the wrong place. The model is consistently wrong. It has learned the wrong pattern. This is underfitting. Bottom left, low bias, high variance. Your arrows are centered around the right area on average, but they are scattered everywhere. Sometimes close, sometimes far. This is overfitting. The model is sensitive to which training examples it saw. Bottom right, high bias, high variance. Wrong and scattered. The worst case. Overfitting lives in the high variance zone. Every time you train on a slightly different dataset, the model changes dramatically. It has not learned a stable pattern, it has learned the specific random sample it was trained on. Total error equals bias squared plus variance plus irreducible noise. You cannot eliminate noise. But you can and must minimize both bias and variance. Why does overfitting happen? There are 4 root causes. First, too many parameters. If your model has 1 million parameters and you are training on 100 rows of data, there are enough degrees of freedom to memorize every single example exactly. The model has more knobs than there are examples to constrain them. Second, too little data. If you train on 100 examples and run 1000 epochs, the model sees those same 100 examples 10,000 times. It has plenty of opportunity to memorize each one. Third, training too long. In the early stages of training, the model learns the real underlying pattern. But if you keep training past that point, it starts fitting the noise, the random fluctuations that exist in your specific training sample but do not exist in the real world. Fourth, noisy features. If you feed the model 600 input features but only 5 of them are genuinely predictive, the remaining 595 columns are noise. The model will incorporate that noise into its weights and overfit. The core problem in every case is the same: model complexity is too high relative to the amount of clean, relevant data available. How do you detect overfitting? You watch two curves. The training loss curve, how well the model is doing on the data it trains on. And the validation loss curve, how well it is doing on a held-out set of examples it has never seen during training. In healthy training, both curves decrease together. The model is learning real patterns that generalize. At some point, the validation curve flattens. The model has reached its capacity. If you stop here, you have a well-generalized model. But if you keep training, watch what happens. The training loss keeps falling, the model is still improving on training data. But the validation loss starts to rise. The model is now fitting noise that is specific to the training set. Every additional epoch is making real-world performance worse. The gap between the two curves at the end of training is your overfitting signal. A small gap, say 2%, is healthy. A large gap, 30-40%, means your model has memorized training data instead of learning from it. The rule is simple. The moment validation loss starts rising consistently, stop. That is your best model. Everything after that point is overfitting. Now let us fix it. There are 5 battle-tested techniques that every machine learning engineer should know. Fix 1: regularization. You add a penalty term to the loss function that punishes large weights. The model is forced to keep its parameters small and its behavior simple. L2 regularization, also called ridge, squares the weights. L1, also called lasso, uses the absolute value and can zero out irrelevant features entirely. Fix 2: dropout. Used specifically in neural networks. During each training step, you randomly set some percentage of neurons to 0. This forces the network to learn redundant representations. No single neuron can become too important. The network learns to be robust. Fix 3: early stopping. You monitor validation loss during training and stop the moment it starts to rise. You restore the weights from the epoch with the best validation performance. This is the simplest and often most effective technique. Fix 4: more training data. This is the most powerful fix when it is available. The more diverse, high-quality examples you have, the harder it is for the model to memorize them. It is forced to learn real patterns. Augmentation and synthetic data generation can help when collecting new data is expensive. Fix 5: cross-validation. Instead of evaluating on a single held-out set, you split your data into 5 or 10 folds and train and evaluate on each one. This gives you a robust, unbiased estimate of true generalization performance. Let us see what this looks like with real numbers. Same task: fraud detection on 50,000 credit card transactions. Same dataset. Same architecture as the starting point, a 12-layer neural network. The overfit model, no regularization applied. Training accuracy, 99.6%. The model is essentially memorizing the training set. Test accuracy on unseen transactions, 63.2%. The gap is 36.4%. This model would be useless in production, worse than many simple rule-based systems. The regularized model, we applied 2 changes. We reduced to a 5-layer network, simpler. And we added L2 regularization with dropout at 30%. Training accuracy, 93.8%. Lower than before, the model is no longer memorizing. Test accuracy, 91.4%. The gap is now 2.4%. Healthy. The regularized model is less impressive on training data. But it is the only one that actually works. The lesson: a high training accuracy is not a success metric. Generalization is the only metric that matters. Here is the complete picture. What is overfitting? A model that memorizes training data instead of learning the underlying pattern. It performs well in training and fails in the real world. Why does it happen? Too many parameters, too little data, too many training epochs, or noisy input features. The model complexity is too high relative to the data. How do you detect it? Watch your training and validation loss curves. When the training loss falls while validation loss rises, that is overfitting. A large gap between train and test accuracy is the signature. How do you fix it? Regularization to constrain weights. Dropout to prevent codependence. Early stopping to halt at the best epoch. More and better training data. Cross-validation for a reliable performance estimate. The goal is not a perfect training score. The goal is a model that generalizes, one that performs almost as well on new data as it does on training data. If this made overfitting click for you, subscribe. Every week we go this deep on the concepts that actually matter in machine learning and artificial intelligence.